Welcome everyone to the Liebherr ITTF Men's Ping Pong World Cup, brought to you right here on ESPN The Ocho, sponsored by Obscure Sports Quarterly. Well, you are in for a treat this afternoon, ladies and gentlemen, because never before have we ever been able to bring two giants of the sport together this afternoon. In the blue will be Jonas von Jonensen, and in the black, Boris McBorns. It's difficult to describe to you the magnitude, the level of greatness that you will witness this afternoon. I mean, this match today is Ali versus Frazier. This is Michael versus Magic in the NBA Finals. This is Hulkamania, Hulk Hogan trying to body slam the immovable object, Andre the Giant. I do not believe I am overstating it when I say that the tremors that resonate from the paddle strikes of these tools of sport will probably cause seismic shifts in the tectonic plates that move underneath our feet. I would not say there is underwater volcanic activity due to the epic battle we are about to witness here today. Why, I remember when I was but a young lad and held the ping pong paddle in my hand for the first time, dreams of an afternoon like this could not even begin to form in the frontal lobe of my brain. As I practiced my forehands and my backhands, my slices, my spin shots. What we are about to witness today is so far beyond the understanding of any ping pong player. I just hope that you can just sit back and bask and get a great ping pong greatness that you are about to witness. Well, it seems like Jonas and Boris are ready to get started. So without further ado, let's get right to the action. But it does seem like Boris, who has been on the offensive for this entire point, is starting to tire. You can see he's down on one knee. Oh, he's staggered. He is sitting on his rear end, returning these pets. Jonas jumps at the chance to end this point. Boris rolling on the ground, diving forward. I have never seen ping pong. He's back on his feet, people. He is back on his feet, and Jonas is hammering away at him. Hammer, chip shot, and Boris, he's running around the table. He's running around. Oh my goodness. Jonas is returning. Oh man, what an epic ping pong battle. So after watching Jonas and Boris duke it out in their epic battle, Mr. Hatzer and Mr. Dahl decided to play a game of ping pong themselves. But they really weren't very good. So the best that they could do was about an average of 12 paddle strikes per point. Well, let's see what 12 paddle strikes per point would look like as a graph, as a table, and also in a formula. So now that we've witnessed our expert ping pong play, let's talk about representing the rate of change from our more amateur appreciation of the sport. In the introduction, we talked about having a rate of change of 12 paddle contacts per 1 point of play. Now, again, we saw in the beginning of this video that the experts would have probably way more than 12 contacts, but you and I are not experts. And so this seems to be an accurate average of what would happen in an actual ping pong match. So we can represent this rate of change in a number of different ways. We can represent it with a graph. Right here, you can see we have the first quadrant of the coordinate plane there. We can represent them as ordered pairs on a table of domain and range values, and we can represent it using a formula as well. First, let's start with a graphical representation of this rate of change. You can see on the y-axis, the vertical axis, we have the number of contacts, and on the x-axis here, we have the number of points. Now, where do we start? Where do we start graphing? Well, let's start with the most basic outcome or possibility, which is if we have played 0 points, how many contacts will we have? Well, obviously, 0 points is going to yield 0 contacts. Now, if we finish 1 point of play, how many contacts will we expect to have had total? Well, we're going to increase from 0 to 12 because we played 1 point. As we then play a second point, what would we expect to happen? Well, if we go up 1 point, we're going to go up 12 contacts. Again, I go up to 3 points, up 1 point, up 12 contacts. And what we see here, guys, is a constant change of going up 12 contacts every time. Oops, got to zoom out a little there. Every time we increase 1 point of play in our ping pong match. Now, what you should also notice is that these points, while roughly sketched by hand, so they're not perfect, do seem to form a linear relationship. And there is definitely a connection, a relationship between a constant rate of change and lines, which we'll explore at another time. So now that we have a graphical representation here, let's move on to a table representation. So if I were to take the same relationship, 12 contacts in 1 point, and put them on a table. Remember, from the graph, the x coordinate or domain are the number of points, and oops, that's not the right word. I apologize. There we go. Let's get that done there. Or the contacts is our y coordinate here. Contacts. There we go. So again, we ask ourselves the question, what is the first point we should start at, the first ordered pair? Well, if we have played 0 points, we will have played 0 contacts. Now, if our domain increases by 1, so notice here, up 1, what would we expect the y coordinates, the number of contacts, to increase? Well, that's what our rate of change tells us is 12 contacts. So my change here would be 12. If I go up another 1 point, I should go up 12 contacts, and so forth. Go up 3, I go up to 36 contacts. Now, what if I want to skip a few? Let's skip a few. Let's go from 3, and let's say the next point is 6. We're not working on a graph. I don't have to follow any specific order. Well, now, this just went up a change of, not 1, of 3. So if a change of 1 point gives us 12 contacts, what would a change of 3 give us? Well, it would be 3 times as many points, so it would have to be 3 times as many contacts. So we can see that 36 plus 36 would give me 72. Let's just see if we want to make a bigger jump. Like let's go beyond what we put on the table here. What if we jump to 12 contacts? All right. Well, if I jump to 12 contacts, that is a change of 6. Well, 6 is doubled 3 here in the points. So that means I need to double my change here. 36 doubled would be up 72, and 72 plus 72 would be 144. So you can see whether we follow this rate of change on the table exactly as a 12-to-1 relationship, or whether we expand that relationship to have more points and more contacts, we follow the same exact pattern. That every time we increase 1 point in the match, we are going to increase the number of contacts by 12. All right, well, let's just prove this one more way with our formula. Now, this is the slope formula that we learned about, and this is a way to calculate the constant rate of change or slope if we know 2 ordered pairs. So let's pick 2 random ordered pairs from our table there. I'm going to go with the ordered pairs 2, 24, and 6, 72. Now, if our rate of change was done correctly on the table as a 12-to-1 rate of change, when we use these points in the formula, we should see that same rate of change yield itself from simplifying our numbers. So let's plug in here. First, we want to decide which ordered pair is x1, y1, and which ordered pair is x2, y2. So now I have decided, again, it does not really matter. It can go either way, and it will yield the same ratio either way, but I chose to make the first order pair first and the second one second. So now let's substitute. Y2 is 72 minus Y1, which is 24, over X2, which is 6, and Y1, which is 2. So my slope, or my rate of change here, is going to be 48 over 4 when I subtract the numerator and denominator. Now, 48 over 4 does not look like 12 over 1 until we simplify that fraction. 48 divided by 4 does indeed simplify to 12 over 1. So this formula here does show me that taking these two ordered pairs gives me 12, a rate of change of 12 contacts per 1 point. And that is how we can represent a constant rate of change graphically as a table or as a formula.